So my name's Glynn Hulley. It's really great to be here as my first Earth hackathon. But just to give some more context behind some recent science results behind urban heat islands, and then also hopefully some motivation for using Ecostress data, and hopefully you guys can understand a little bit more about how we actually derive the temperatures that you're using. So getting on right into it. So I always like to show this map with urbanization, and it's a really spectacular image of Earth's city lights from the NASA Defense Satellite Program. And so just a couple of stats here. As everyone knows, the world's experiencing rapid urbanization. City populations are forecast to double from 2.6 to 5 billion by 2035. And by 2050, the forecast is that almost 66% of the world's population will actually live in cities. It's interesting on the map too is that the intensity of the lights don't necessarily correlate with the density of populations, right? So if you look at India and China, the intensity of lights is not as bright as Europe and the US, and yet they have obviously the highest population. So that was an interesting fact from the map. So moving on, just to try and understand, the man-made surface, how man-made surfaces alter not only the surface but also the atmosphere. So in urban areas, the conversion of the natural landscape from vegetation into man-made urban structures such as roads, buildings, and so forth, it drastically alters the surface energy balance budgets of urban areas and also the local climate. And it does this in four key areas. One is the main thing is a decrease in the evapotranspiration, right? So you're converting natural vegetation into urban surfaces, and so less vegetation means that you're reducing the evaporative cooling that vegetation has to the atmosphere, and the release of latent heat flux, which actually cools the air. And so when you take away the vegetation, you obviously increase the air temperature of the surface through the man-made materials. And the second way is through you also have a reduction of sort of thermal radiation escaping the surface areas through turbulent heat transport, right? So you've got these city canyons, and what happens is the radiation just bounces back and forth between buildings and gets trapped in these sort of street canyons, resulting in heating of the air and increased urban heat island effect. The third way is through anthropogenic heat emissions themselves. So think of air conditioning, automobiles, heating generators, power plants, and so forth in the cities that actually heat the air through human interaction and activity. And so this is usually a smaller component, but it does have non-negligible effects in, for example, northern latitude cities and colder areas where more heating is required in peak times during the summertime. And then lastly, of course, air pollution. So what is it about urban surfaces that result in the heating of the surface and the urban heat islands? So obviously urban surfaces have properties that directly modify the surface energy balance, as I mentioned before, resulting in heating of the air relative to the surrounding rural areas. So rural areas which have more pervious surfaces compared to urban surfaces, think of asphalt, concrete, roofs, those kind of materials. And there's really three primary properties that results in these materials heating the air. And they are, firstly, they have a higher thermal conductivity, so the ability to transfer heat back and forth. And then the last two here are really important. There's almost a double whammy for urban heat islands, is that they also have a higher heat capacity than obviously vegetation, so they're able to store heat more efficiently. But they also have a lower albedo, which is another fancy term for just solar reflection, right? So the ability to reflect solar radiation is much lower than vegetation. And so they're absorbing more solar radiation, but they're also storing that radiation more efficiently. And then what happens is these surfaces with high thermal mass, they store that energy during the day, and then they slowly release it during the nighttime, resulting in the urban heat island effect. So many of you have probably seen this image. It's a classic image that's probably been shown millions of times, but it's an image of an idealized urban heat island profile. And here what I've basically done is I've just sort of tried to show the components of the surface energy balance that result in the urban heat island, right? So the net radiation at the surface, which is primarily driven by the solar radiation, has really three pathways to be expelled, right? So one is latent heat, which, as I mentioned before, is the transpiration from plants and vegetation, resulting in cooling of the air. So obviously that component is larger in rural areas. Secondly, you have the energy that gets transferred into actually heating of the air, which we call sensible heat. And so that's obviously lower in rural areas and higher in urban areas, because you have more urban surfaces, as I mentioned, that store heat and then re-emit that radiation into the air. And thirdly, into ground storage. So this is the energy that gets directly stored in the ground and could be released later. And so this is also has a larger component in rural areas and a smaller component in, a larger component in urban areas, smaller in rural. And then you also have the waste heat, right? So this is anthropogenic heat emissions from air conditioning and so forth. So all of these components lead to higher temperatures in urban areas relative to the surrounding rural areas, both day and particularly during the nighttime. So moving on to heat waves. So we've been performing a study on heat waves at JPL over the last couple of years, and some of these results were recently published. And what we found is that in Southern California, particularly in urban regions, what we're finding is that we're seeing these rapidly increasing trends in heat wave metrics in terms of their frequency, their duration, their intensity, humidity, you name it. All the metrics are increasing at really significant rates. And I've just shown two examples here of frequency and duration. And so, for example, you can see during the 21st century, we're getting up to almost 8 heat waves on average per year, lasting, upwards from 6 to 9 days in length. And, back in the 20th century, we were getting only about 3 heat waves per year, lasting about 3 to 5 days. And, here in Los Angeles, just in the last 3 months, we've already experienced about 5 heat waves, and we have a total of almost 8 already this year. So it's turning into almost a record-breaking heat wave here in California. And one of the most disconcerting results that we found too was that not only are the frequency, intensity, and so forth increasing, but the humidity of the nighttime heat waves in Southern California are really becoming much more hotter and humid. So the left plot here is just showing that if you look at the temperature of heat waves in green, this is the nighttime temperature, and this is the trend from 1980 to present day. And then if you fold in the water vapor content, which we, sometimes you probably have heard of, is called the heat index. So it's basically the thermal comfort that you would feel as a human by introducing the effects of humidity. And you see that trend is actually much steeper than just the regular temperature trend, almost double that of the regular temperature trend. And so we dug a bit deeper, and what we found was that there's this very strong moisture anomaly source just off the coast of Baja, California. You can see this big red blob on the right side. And what happens during the heat waves is that the usual northwest flow of surface winds changes from the southeast direction, which kind of advects all of this moisture into the Southern California region. So, for example, the August 14th heat wave this year, it's very, very humid heat wave, everyone was complaining for, and it lasted very long as well, about 2 weeks, so it was very uncomfortable. And this has obviously is a major concern for people with chronic illness, the elderly, and so forth, because they're unable to cool off during the daytime and then recover from the high daytime heat, because the nighttime heat is almost just as warm and also very humid. And this is one of the biggest results in deaths from heat waves. And so if you look at, this is from NOAA, the National Hazard Statistics. A lot of people don't realize that heat is actually the biggest killer in terms of all natural disasters in the USA. This is in 2017. But if you look at the 30-year averages in yellow, what you can see is that heat accounts for more deaths than both hurricanes and tornadoes combined, which is pretty incredible. And the reason for this is that they're silent killers, right? So we can't see the heat. We can see tornadoes and hurricanes, obviously. And so they're less glamorous than the other natural disasters. They don't make the news media as much, and also affect more sort of the forgotten communities, right? So the elderly, the poor, and so forth. So moving on to how we actually measure not only heat waves, but also urban heat islands. We use thermal radiometers, either airborne or from space or from the ground. We can use thermal cameras. And what we measure is something called the surface skin temperature, right? So it's not the air temperature that we feel just by walking around, in the air. It's the temperature that you feel if you actually put your hand on the surface, so the actual skin surface. It's central to the surface energy balance, since it controls the amount of heat flux emitted into the atmosphere. As I said, it modulates the air temperature above it. So the hotter the surface is, obviously, the hotter the air above it is going to be. And that obviously affects the energy exchanges relating to thermal comfort. And from the surface skin temperature, we can compute the surface urban heat island, which is what you guys are doing right now with Ecostress Data in the hackathon. So just one or two slides here briefly on how we actually compute the surface skin temperature. So this is the classic electromagnetic spectrum that you guys are probably kind of familiar with, or learned from school. And what you can see is just the range of energy, ranging from high energy X-rays at higher frequencies all the way to radio waves at much longer wavelengths and lower energies. And so obviously with the human eye, what we can see here is visible light from about 0.4 to 0.7 microns. And what we're really interested in here is to determine the temperature. We need to be looking a little bit at longer wavelengths, around 10 microns. So this is what we call the thermal infrared region. And this is the region that Earth emits radiation primarily in. So if you look at the green at the top there, Earth emits at about 300 degrees Kelvin, whereas the sun, the incoming solar, at much higher temperatures comes in the UV, so much shorter wavelengths. And so it's this thermal infrared that's the focus of us being able to calculate the land surface temperature of the Earth. And it's basically radiation that we can feel, right? But we can't. If you put your hand above a stove, for example, you can feel the heat and radiation. Or as I like to say, if you have predator thermal radiation eyes, obviously you can see thermal radiation. And so how do we actually calculate this? So this is I promise you this is the only equation that I'll show here, but back in the 1900s, a famous physicist called Max Planck came up with an equation that described the radiant energy emitted from any surface object above absolute zero, right? And so this energy is related to both the wavelength that you're measuring it at and also the temperature of that surface. And so what I've plotted here is just these functions at different temperatures. And if you look at the TIR here, right, so the thermal infrared between 8 and 12 microns, you can see the temperatures of the Planck function range in typical sort of Earth-like temperatures, -23 upwards to 60 degrees Celsius. So if we place a radiometer with detectors that are sensitive to radiation in that region, we can observe the radiation emitted from objects, and we can then basically solve for the temperature in that equation to be able to derive what the temperature of that object is. And obviously it's a little bit more complex than that, because the radiation that we observe from space goes through all kinds of absorption and attenuation in the atmosphere, and so we have to account for that before we can, what we call an atmospheric correction of the radiance, before we can actually retrieve the surface temperature. But what you're seeing from Ecostress data is this temperature that we solve for in this equation. So speaking of Ecostress, it stands for the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station. And so it's obviously on the International Space Station, as you can see in the image, actually along with a couple of other NASA instruments, as well on a module called the Japanese Experimental Module. And so you can see an image of the actual instrument on the left there at JPL while it was going through a testing phase. It has a scanning radiometer that basically scans the Earth back and forth, and then transmits that light into a telescope, which gets transmitted onto the detectors, and then that's how we measure the thermal radiation. And so with Ecostress, just like a normal camera, we take snapshots of the Earth. They're pretty wide, about 400 kilometers wide. In terms of the pixel size, they're roughly about 70 by 70 meter square pixels, so roughly about the size equivalent to about a football field. And obviously there's, the pixel array goes across the 400 kilometer scene, and then we take multiple snapshots around the globe in these sort of scenes. Now, there's two things that are unique about this instrument. One is that it's the highest spatial resolution currently available to determine temperature from space, 70 meters. And the other is that the ISS has this really weird precessing orbit, right? So typical satellites will come over at the same time every day, but the ISS comes over at different times every other day, right? So this enables us to measure temperatures at different times throughout the day through each overpass. So this just shows an example throughout the year. We can see temperatures at different hours of the day throughout the year. And this changes with latitude as well. But it really is powerful because it enables us to image the diurnal cycle. And then, as I mentioned before, the detectors are placed in this thermal infrared region from 8 to 12 micrometers. We have 5 different bands there that measure the emitted radiation from Earth. And then from those 5 bands, we were able to determine the temperature. This is just a nice image from the launch from Cape Canaveral in Florida, launched on a SpaceX Falcon 9 rocket. It was a really beautiful experience. This was my first launch I've ever seen, and it was a really perfect conditions, beautiful morning. You can see the stage 2 separation there of the Falcon 9 rocket. And then this is the, when it's separated, the Dragon actually separated from the main rocket. You can see Ecostress there. It's sort of the white box. And it's about the size of a small fridge, basically. That's the size, and you can obviously can't see the instrument there because it's enshrouded in the box. This is about a day later. It was captured by the ISS and then installed on the Japanese experimental module along with a couple of other instruments. Ecostress is sort of the white-looking newer box there, jutting out. And so this module is sort of separated away from the main ISS solar panels and all the other stuff a little bit so that we have an unobstructed view of the Earth. And then this is the Ecostress science team, where obviously we're very happy that morning that we had a successful launch. So moving on to actually looking at some Ecostress data. As Josh mentioned earlier, if you guys were listening, it's mostly driven to looking at ecosystems and plants and how plants use water, and also how plants respond to stress, right, from droughts and so forth. And it's also, from the applications point, it's very useful because we can inform farmers, for example, on how much to water and also when to water their crops based on the evapotranspiration that we derive from Ecostress. But obviously it has a lot of other science uses. Here I've just highlighted a few. Volcanoes, we can determine the SO2 from volcanoes. We can image wildfires. We can look at coastal water currents. But obviously the focus here is looking at urban heat islands. So it's been a pretty popular topic. The Slack channel is full of examples of people that have used it to image urban heat islands all around the world. And so moving on to what an actual Ecostress land surface temperature scene looks like. So this is the 400 by 400 kilometer sort of snapshot that I showed you before. And this is one of our first scenes, actually, one of our first orbits on the 22nd of July, soon after launch. We had this really nice image over Southern California. And just pointing out a couple of landmarks here, you can see clouds are usually cold in the thermal infrared, right? So whenever you're looking at the data, clouds are usually below about 280 degrees Kelvin. And if you want to do the conversion there, it's just minus 273 to get to Celsius. This is an early morning image, so you can see the Sierra Nevadas are very cool. So the higher elevation areas are cooler. You can see this very warm area around Death Valley, obviously, is the hottest surface during this time. And then so you can see the Mojave Desert is a bit hotter, and the Salton Sea is also quite warm. The water is warm because it has a high thermal mass. And so it stores that heat in the day, and then it stays warm at nighttime. This is a zoom in of that image to the Los Angeles area. So if anyone is looking at Los Angeles, these are the kind of maps you'll be wanting to generate. And this is really a one-of-a-kind image because it's the first time we imaged LA at this time of day, so at 4 a.m. And so we weren't sort of aware before is that if you look at the freeways and asphalt and objects with high thermal mass in the city, you can see how much energy they're still radiating. Even at 4 a.m., this is during a heat wave in July. And so it is really fascinating to see the roads and freeways just really stand out. And then you can also see kind of some fine scale temperatures like power plants, near Long Beach. You can see the high temperatures from the smokestacks, for example. Then also beware of clouds, right? So over LAX right here, you can see quite a cloud bank coming in, probably from the marine layer. And so don't be confused between clouds and actual cooler surface temperatures. And typically you can qualitatively see that they have kind of the shape of clouds, right? So this map actually made the NASA news. It's the first time we've obviously seen temperatures of the urban areas at this time, and then also over the diurnal cycle. So on the left, you can see a sort of a snapshot of temperatures throughout the day, throughout that heat wave towards the end of July. And you can it's kind of cool to see the sort of the evolution of temperatures as they evolve throughout the day. We also made the news when we imaged the famous European heat wave in 2019. We imaged a couple of cities, Rome, Madrid, Paris, Milan. At that time, the ISS was coming over at early morning hours, so we were able to look at really look at the urban heat island with urban surfaces with regard to the rural background much clearer. We imaged the record-breaking heat wave in LA. Recently now in August 14th, and then also the famous 130-degree highest temperature ever recorded on Earth in Death Valley. So I'll just sort of kind of end here by looking at a couple of heat mitigation and adaptation strategies that, for example, the LA County Sustainability is working on. Two of them are cool pavements and cool roofs. Here, cool pavements are basically they're painting streets with this high reflective paint emulsion, which reflects the solar and results in cooling. And then cool roofs is simply painting roofs whiter and more reflective colors, and also installing solar. They're also looking at identifying optimal locations for cooling centers using the Ecostress data, and then issuing extreme heat alerts. So this is kind of interesting. This is a thermal image that I took from a thermal camera in the San Fernando Valley during a heat wave. This is during the afternoon. I was at a friend's place of mine. And you can just see the drastic difference between the temperature of the roof during this time and the rest of the house and the vegetation. And my friend had sort of this black shingle roof, right? So it is probably the worst roof you can have in terms of both absorbing heat and not reflecting as much solar. And so he got such a fright when he saw this that he decided to paint his roof with a white paint, basically. So he spent a couple of days painting the roof, but he also left a little bit of the dark shingle left here, which you can see on the photograph that I took on the left. And so if you look at the temperature difference there, from the thermal camera, it's almost 30 degrees, which is really incredible. I had no idea it would be that much. 30 degrees is a lot. And what he claims is that, you know, during heat waves now, he barely has to use his air conditioning. And so it's not only good, obviously, for thermal comfort, but also for reducing energy consumption. And then probably what the LA City Council have been working on the most are these cool pavement projects. So they've contracted out the Bureau of Street Services, and they paint the surface with something called Cool Seal. It's a type of reflective paint. And this is an example of a Stephanie Drive in the Winnetka neighborhood that they painted basically at neighborhood level, so several streets. And I do have actually a full list of streets that they have painted in LA if anyone's interested in actually going and pinpointing some of those streets and seeing if they can see any cooling. But what I did was firstly I went out with a thermal camera and I found about a 12-degree difference between the painted street and the regular asphalt. And then I went in and actually looked at some Ecostress data. So this was during the heat wave actually in August. This is a nighttime image. And what you can clearly see is this sort of crescent of cooling, you know, in the vicinity of those painted streets in the Stephanie Drive area. So there was definitely a cooling that we could actually see from the Ecostress data. And obviously they were very excited to see this, that we can actually quantify this from space as well. And so this is kind of the final result here is when you look at the temperature distribution in green of the neighborhood within the cool pavements, and then if you contrast that with the rest of the neighborhood in red, you can see that there's about an average of about a 2-degree cooling of the neighborhood with the cool pavements applied. And we see that both on the daytime on the left and also the nighttime on the right. And so this result was actually presented yesterday to California legislators in Sacramento in an effort to advocate for more expansive funding and painting of neighborhoods in both LA and also other cities in California. And I guess I'm going a little bit over right now, but the last few slides, I'll just show you some examples of the downscaling or sharpening technique where we actually increase the spatial resolution of the Ecostress data. And we do this by using what we call LST predictors. So these are other types of variables that have a higher spatial resolution that we can get from, for example, the Landsat satellite. And these include vegetation indices, albedo in terms of reflectivity, climatology, and so forth. The two that I focus on are the vegetation index, which you see on the left, and then the reflection or the albedo on the x-axis. And what I plotted here is the temperature in terms of pixels, looking at the relationships between those three variables. And so you can see quite a well-behaved relationship there. Reflective roofs are cooler and have a higher reflectivity and lower NDVI or vegetation index, while vegetation has a high vegetation index and low albedo and is cooler. And then other roads and parking lots, and they have both low NDVI and low albedo. So if we put that into a neural net machine learning algorithm or a multivariate regression algorithm, and we can train the algorithm using Ecostress data and then Landsat higher resolution albedo and NDVI, we can come up with a training model. And this is kind of what the result looks like. So in the middle are the native resolution Ecostress data at 70 meters, and on the right is kind of the sharpened up version of the data. So you can really see, you know, in the top right, you can see golf courses coming out, and you can now discriminate between roads and other surfaces and roofs. And so it's really quite a powerful technique. And this is another image just showing in black and white how roads kind of and roofs really stand out when you employ the thermal sharpening. So we have posted a tutorial on how to do this. It does take a little bit of programming, either in MATLAB or R. And then in a similar way that you grab the Ecostress data from up here, you can do the same for Landsat and then apply the thermal sharpening, and you can really improve on your urban heat island maps. And sorry for going over, that's all I have. If there's any questions, stay cool and hack away.